So this is lab 3, magnetic field of a bar magnet. In this lab, we are measuring various distances that produce a specific component of the magnetic field from a small bar magnet. And by doing so, we can determine the distance dependence and calculate the magnitude of the magnetic moment of our magnet to use in our glow strip code. And we're also finding the off-axis magnetic field and comparing that value to the calculated magnetic field from our glow strip code. This is just a little summary of our results, which I'll get into later. So for our procedure, we first wanted to find the distance dependence, and we did that by taking our phone and the magnetometer app and running that parallel to our meter stick and our magnet to find the distance where the magnetic field in the x direction had an absolute value of 20 microteslas. And then we repeated that for these other distances. And then for our off-axis point, we wanted to find d in the components of the magnetic field. So we did that by first finding distance d perp, where the net magnetic field had a magnitude of 100 microteslas. And we used that to find d, distance away from the magnet, and the components of the magnetic field at that point. We used the fundamental physics principles of magnetic field distance dependence, which follows this formula, and magnetic field of a dipole, which follows this formula. And we noticed that the magnet produces a magnetic field in addition to Earth's magnetic field, so we need to compensate for the presence of Earth's magnetic field by orienting it the right way. We also observed that when the magnetometer is far away from the magnet, it measures the near zero magnetic field in the x direction, and as we move the magnetometer closer to the magnet, the measured x component of the magnetic field increases. So to find mu, we took our values that we found in our experiment and graphed them with the log of the distance dependence formula, where we got n with the slope and lnk with the y-intercept, which we used to calculate our mu using this formula here, where we have 2 mu because we're doing an on-axis calculation, and we were able to find that our mu would equal 2.01 meters squared. And then we use that value in our coding for the magnetic field around our magnet. So we inputted that here, and we created the magnet at the origin, as displayed right here by this white cylinder, and then we created the magnetic field function using the earlier formula that I showed for dipole magnetic field. And then we just made observation locations both parallel and perpendicular to the magnet and made arrows at each observation location so we could see how the magnetic field looked like for the magnet. We also wanted to find the magnetic field off axis, so we put in our d perps here and then found the distance away from the magnet that we needed to be and found the measured magnetic field components doing that. And we found by corrected because we had to take into account Earth's magnetic field. So we did that by adding by measured to by Earth because by Earth was negative to get our corrected value. And we were able to find that B net would be 3.85 times 10 to the negative fifth, which we then compared to the value we got while coding. So to code this, we just inputted our average d perp and then found an observation location according to that d perp and found our r vector doing this observation minus source location and found the magnetic field at that point using our function from earlier. And we were able to model that like this. And we could see that we got these components for our magnetic field at 45 degrees away from our magnet with the distance d. And we saw that our magnetic field for in the x component is a little bit off, but our y component magnetic field is pretty similar. And we were able to see that the magnitude overall is pretty similar to the experimental magnitude that we got. So what if we hadn't oriented our experiment to compensate for magnetic Earth? Then the magnetic field would be skewed depending on how the orientation is set, as we mentioned earlier. And what if we were to stick two identical magnets together? Then the measurements would increase because the magnetic field becomes stronger with two magnets. Overall, we were able to find these results, and our Glowstrip code connected the relevant physics principles to the model used to represent our real system, and it showed how the magnetic field would look like on the magnet and allowed us to see the theoretical magnetic field at an off-point axis location as well.